Well, welcome everyone. It's great to have Virginia Vassilevska Williams as our last speaker of the semester. Before we move on to the talk, let me first thank the operating team. So we have in India with me today, who's operating the talk, and then behind the scenes we have Clément Canon, Gautam Kamat, Thomas Hollenstein, and Oded Regev helping us out. So maybe in India, you want to introduce the groups who are joining?
Yeah, thanks. I will introduce the group now. So we have the group from Rutgers here. Hey.
Hi.
We have Anushesh from Texas A&M. Okay,
Hi.
we can't see your video.
I can see.
We have Debbie from Michigan.
Hi.
Okay, we again can't see you. Then we have Huck from NYU. We can actually see you. And then we have the group from Santa Fe.
Hi, yeah. How are you?
We have K. Gopalakrishnan from East Carolina. Then we have the group from Caltech. Okay. And they have made it very clear that they are from Caltech. Then we have Sai from Buffalo.
Hi.
Okay. And we have Ramanujan joining. So, okay, so we're done with the groups. Thank you.
Okay.
Okay. Thanks in India. So welcome, Virginia. So it's a pleasure to have Virginia as last speaker for the semester. So Virginia got her BS, usually I don't mention this, but from Caltech, 2003. Then she got her PhD from Carnegie Mellon in 2008, and then she was a postdoc a little bit at IAS and a little bit at Berkeley. And now she's, since 2011 or 2013, she's a assistant professor in Stanford. So Virginia is most famous for her work on improving the exponent for matrix multiplication. So the first exponent on Coppersmith-Winograd was her work. But in general, she's really done a lot of work, impressive work in algorithms. So this semester, she was co-organizing a semester at the Simons Institute in Berkeley on what they call, fine-grained complexity. And this is a very interesting recent line of work where Virginia and collaborators and others have been proving strong lower bounds on polynomial time algorithms based on different conjectures than the, Anyways, she's going to tell us much more about it in her talk. So welcome, Virginia. It's a pleasure to have you.
Thank you. Thank you. It's a real pleasure to be invited to give a talk at TCS Plus. It's great. Thank you so much. So today I'm going to tell you a little bit about fine-grained complexity, and what I'm going to do first is I'm going to give you an introduction of the area and a summary of what is known, and then I'll go into some really exciting new results that we have. So let me start with a little bit of a corny slide. Okay, so here's a situation that happens in the real world. So we have a scientist and a computer scientist on the right. The computer scientist, well, that's the best picture I could find. Okay, so the scientist says, I ran all these experiments, I got a ton of data, and I want to solve some algorithmic problem. But I'm really stuck. I tried a lot of algorithms. I even looked at papers. I couldn't find anything. So please help me. And then the computer scientist says, oh, I'm really sorry, this problem is NP hard. If you get a really fast algorithm that always works, then you'll solve a really hard problem in CS and math. So I'm sorry. And then the scientist said, okay, I feel a bit better because what I tried didn't work. So okay, I'll just use some heuristic and hope for the best. All right, so this is something that happens a lot. But then, what happens to some other easier problems? So now the scientist comes in and says, I have this data, please help me with this algorithmic problem. Computer scientist says, great news, I have an n-squared time algorithm. And the scientist said, oh, but I can't run an n-squared time algorithm, my data is enormous. Can you give me a linear time, a sublinear time algorithm? And the computer scientist says, oh, I don't know. Aren't you happy with n-squared time? N-squared is already fast. I can't give you any reasons. And so what do we do now? So we don't have a compelling reason why we're stuck at n-squared, and we want to have one. So this is sort of a funny pictorial representation of what we're getting at. Okay, so in theoretical computer science, we typically think of polynomial time as efficient and easy, but this is not because we think all polynomials are easy. It's because of other very technical things. For example, when you compose a fast algorithm, you want the composition to also be a fast algorithm. So composing two algorithms should yield a fast one. Also, just focusing on arbitrary polynomials yields some model independence. So whether you solve your problem on a Turing machine or a RAM, when we only care about polynomial runtimes, this doesn't matter. So, okay, but no one really believes in n to the 100 is fast or n squared even. So, yeah, so when we have an n squared time algorithm, an n cubed one, but we can't improve, and how do we explain why we're stuck? Okay, so to get to this question, first I'm going to say what I consider fast in this talk. I say that the easy problems are the ones that we know how to solve in n squared times polylog n time on a RAM. I'm going to fix the computational model because I want to care about the exact runtimes. So you can have a similar, yeah.
Is this because you care so much about matrix multiplication, or it's just everything that you say would be applicable to any exponent and it's just arbitrary for the talk?
Arbitrary. N squared is arbitrary. In fact, it doesn't even have to be polynomial in general. I can fix 2 to the n, 3 to the n, n cubed, whatever. Here I'm just going to talk about n squared because there's a lot of interesting problems there already. So, okay, so let's just talk about n squared for now, and then we'll see some other examples later on. Okay, n is the size of the input. Good. So here's a slide. What do we know about n squared time? It turns out we know a ton. There's a lot of really cool techniques that we know how to employ. First of all, there's classical algorithms that solve very complicated problems. For example, min-cut, single source shortest path, and so on, and they run in almost linear time. Then we have recent breakthroughs that achieve very close to linear time as well for even more complicated problems, and they're very, very sophisticated and awesome techniques. And we even have sublinear algorithms and property testing and so on. So we know a whole lot, okay? Unfortunately, even though we have developed all these awesome techniques, there's many problems in polynomial time and outside of polynomial time where there is some easy algorithm that runs in f of n time. For polynomial time problems is, let's say, n to the c for some constant c. But somehow this n to the c is some bottleneck, maybe for our techniques or maybe for something else, and we don't know how to improve it, and there's been no improvement in decades. So I'll give you a few examples to see what's going on here. Okay, so for n squared time in particular, there's no n to the 2 minus epsilon time algorithms known for the following types of problems. Many problems in computational geometry, for example, the very simple question, given n points in the plane, are any 3 of them collinear? So this is something that's asking, are the points in general position, and you need to solve this primitive every time you run a computational geometry algorithm. So for this problem, there is an n squared time algorithm where n is the number of points, and there's nothing really better known. Okay. In a completely different area, in string matching, there's a ton of problems where we don't have very fast algorithms. We have n squared time, but not better. For example, edit distance on 2 sequences of length n, sequence local alignment, longest common subsequence, and so on. So let me define a few of these. So these are sequence alignment problems. So for example, in computation geometry, you may be given 2 strings over some alphabet, let's say the 4-letter alphabet. And we want to know how similar are these sequences and what do they have in common. And as you can imagine, there's many definitions of what similarity means. So for example, there's edit distance, which is a very commonly used definition. There's longest common subsequence, local alignment, and many others. So here's longest common subsequence. This is arguably the simplest problem out of these. So you're given 2 sequences, and you want to find a subsequence that appears in both of them, and it has maximum length. A subsequence is just a string of letters that appear in the same order in both of the sequences, but they may skip some letters. For example, here the longest common subsequence are the blue letters, and the red letters are removed. And you can think of this as a matching problem because you want to match all of the blue letters one to another. Now, this problem has a ton of applications, not only in computational biology, but also in spell checkers. It has a classical n-squared time dynamic programming algorithm we study in, we actually teach in our algorithms courses. And there's the best known algorithm, shaves a little bit off this n-squared, so it has an n-squared over log squared of n at runtime by Masek and Patterson. And this problem, as I said, is solved daily on huge strings. And if you want to solve, just run it on the human genome, for instance, it has 3 billion base pairs. They don't typically run it on the whole genome, but on substantial fractions of it, and that's already too slow. Okay, so this is a very important problem, and we want to understand why we're stuck at n-squared. Okay, I will talk a bit more about this problem later in this talk. So let me continue in giving you one or two more examples of very important fundamental problems for which we're stuck at some runtime, namely n-squared. Okay, so we had computation geometry, string matching. There's many graph problems in sparse graphs. So you're given a graph on n nodes, order n edges. For example, I want to know what the diameter is. The diameter is the largest distance. And you can obviously solve it in n-squared time by running all pair shortest paths. It's a very fundamental problem. It has a lot of applications again, but even just approximating it in faster than n-squared time seems to be very hard. Okay, so that's another problem. Another one. Now, if you look at all pairs problems in dense graphs, for example, all pair shortest paths, diameter, radius, and so on, in dense graphs, they require n cubed, where n is the number of nodes, but the input size is n squared because the graphs are dense. So now instead of on n squared time, we're stuck in n to the 1.5. So you have a lot of runtimes at which we have some algorithm, and then we're stuck, and we don't know why. And the question is, why are we stuck? Are we stuck because of the same reason? Is it because we just don't have the correct technique, and when you find the technique, we're going to resolve them all? And more importantly, how do we even begin to address this? Okay, so in order to do this, we thought, okay, how do we address this for the hard problems, the NP hard problems? So let's look at a canonical hard problem, KSAT. You're given n variables and a formula which consists of m clauses. Each clause is just of the form y1 or y2 and so on, where each yi is a literal, so it's a variable or it's a negation. And now what you're asking here is to find a Boolean assignment to the variables that satisfies all the clauses. And okay, we have that this problem has a 2 to the n time algorithm. You just try all the possible assignments. And the best known algorithm is, again, 2 to the n. You can shave a little bit off the exponent that depends on the width of the clauses, but as the width of the clauses grows, this runtime is still 2 to the n. So this problem is, an exponential time problem that has the same behavior as the polynomial time problems that we care about, in the sense that we have some trivial algorithm and we don't know how to improve it. Okay, but when we ask why is KSAT hard, we say, well, it's hard because it's NP complete. All right, we don't say because we don't know how to improve this trivial algorithm. We say it's because it's NP complete. And what does that mean? It just means that if you had a fast algorithm for it, namely a polynomial time algorithm, then all the problems in NP also have polynomial time algorithms. So P would be equal to NP. That's a really hard problem. And really, all of the NP-complete problems are considered hard because fast algorithms for them would imply faster algorithms for many important problems, and that's considered very surprising. Okay, so we want to do something like this for the polynomial time problems. Now, in order to address the hardness of NP-complete problems, we use polynomial time reductions. We cannot use anything like this for the polynomial time problems because that would destroy the runtime, and we have to be more fine-grained. Okay, so here's what we've been doing. The idea is we identify some really key hard problems that we really, really believe are hard, and then we reduce these in some way to other such problems, And then we can say if these problems have a fast algorithms, then the key problems also have a fast algorithm. And so we can say that this is surprising, and therefore that we have some lower bound conditional. And then in the end, we hope to find some equivalence classes. So things like if all these problems in this set all require n cubed time, or they can all be solved in n cubed time, something like this. And we'll see examples of this. I will go through these numbers one by one. So first I will talk about the key problems that we have been looking at. I'll tell you what reducing means, what type of reductions we need. And then I'll show you a picture of what we know so far. Okay, let's start with the first one. Now, as I mentioned, CNF SAT is hard, it's NP hard, but it's also conjectured to be really, really hard. In particular, here's two conjectures. The first one is the exponential time hypothesis. This is by Pagliazzo, Paturi, and Zane. And the exponential time hypothesis says that 3-SAT in particular requires exponential time. So there's some constant delta so that you can't solve it faster than 2 to the delta n time, where n is the number of variables. Even stronger, the strong exponential time hypothesis says that 2 to the n is essentially optimal for k-SAT. So for every epsilon, there's some constant k, such that k-SAT cannot be solved in 2 to the 1 minus epsilon to the n time, times polynomial in the number of clauses. So strong ETH is a very, very strong variant of ETH. In fact, we know that strong ETH implies ETH. So instead of using P not equal NP as the conjecture, we can use ETH or strong ETH as the conjecture to base hardness on. So this is one option. And a lot of reductions to polynomial time problems use strong ETH in particular. Okay, but these are not the only key hard problems we could try. For example, there's a problem called threesome, which has been very popular in the computational geometry community. Here you're given a set of n integers, and you want to know if 3 integers in the set sum to 0. It's a threesome problem. A completely different problem is now you're given n vectors of dimension d, where d is slightly more than logarithmic, and you want to know if 2 of these vectors are orthogonal. And finally, a completely different third problem is the classical all-pair shortest path problem. You have a weighted, maybe directed graph, and you want to compute all the distances between every pair of nodes. So these problems are different, and I'll just mention a little bit about each of them. So threesome again, n numbers, you want to know if 3 of them sum to 0. This is a very simple n-squared time algorithm. You can think about it. It's something that our students get asked in interviews, apparently. And for integer inputs, Baran, Dimane, and Petrashko showed that you can also get an n-squared over log squared n time algorithm. There's some polylog logs I'm omitting. For real numbered instances, a more recent result by Gronlund and Petty showed that you can shave a log n factor even for real numbers. So this is now on the real RAM. So there's this threesome conjecture because people have tried so hard to improve on this threesome problem, and it's so simple. Now there's this threesome conjecture that has been formulated many, many times, and it says that threesome on n integers, even when you restrict them between, oops, this should be minus n cubed and n cubed, not 1 over. Anyway, between minus n cubed and n cubed, threesome on n integers, that requires essentially n squared time. You can shave polylogs and n to the little of 1 factors, but you won't be able to do better than n squared. Okay. So this is threesome. Orthogonal vectors, again, it's a problem of n vectors of very small dimension. All of them have 0 and 1 in their entries, and you want to know if 2 of them are orthogonal. This is a pretty much trivial n squared times d algorithm. You just actually compute the inner product of all pairs. And the best known algorithm shaves something over this n squared, but what it shaves depends on the dimension. So for example, if the dimension is logarithmic, you get a truly subquadratic time algorithm. But if it's slightly more than logarithmic, it still ends n to the 2 minus little of 1. And very, very sophisticated techniques come into play here. Now, the orthogonal vectors conjecture says that the orthogonal vectors on n vectors requires n to the 2 minus little of 1 time, and all these conjectures are on the RAM model, as I mentioned earlier. Okay, so what's known as Ryan Williams showed in 2004 is that the strong exponential time hypothesis about CNF SAT actually implies this orthogonal vectors conjecture. And so if you believe that SAT is hard, then orthogonal vectors is hard. And in fact, orthogonal vectors might be hard even if you can improve on the 2 to the n algorithm for SAT. So orthogonal vectors, this conjecture is actually safer to use in hardness reductions. Okay, and the final problem, all pair shortest paths, we all know what it is, and it has a very, very long history. On this slide, I only show some of it, and if you notice, there's always this n cubed popping up, n is the number of nodes. And Fredman in the 70s showed you can shave a little bit of the n cubed, and many, many logs were gotten rid of until in 2014, Ryan Williams showed that you can actually shave all possible polylogs. You can shave an 2 to the order square root of log n factor, but unfortunately, this n cubed is still there. And this motivates this conjecture that all pair shortest paths on n nodes, even when the weights have order log n bits, requires n to the 3 minus little of 1 time. Again on the RAM. So these are all the conjectures, and practically all of all the reductions, with some small exceptions, to polynomial time problems start from one of these or from KSAT. Okay, so now we've covered all of the problems that we have tried to blame for the hardness of polynomial time problems. Okay, so one final note is why do we think that we need so many hard problems? Why aren't they just all equivalent? And it turns out that some recent research suggests that these problems are not equivalent. In fact, if you assume a slightly stronger version of strong ETH, you can show that orthogonal vectors cannot be reduced, threesome or all pair shortest paths. So it's either incomparable or it's harder. And in the way that this result sort of proceeds, it says that there is actually a very fast non-deterministic and a common non-deterministic time algorithm for threesome and all pair shortest paths, but we believe that there isn't one for orthogonal vectors. Okay, so there's some reason to think that these are not equivalent, and this would be why some reductions go from one of these problems but not from others. Any questions until now? Okay, so I've covered the first part, identifying key problems that seem hard, and now we want to reduce them to other such problems. Yeah.
So this conjecture that you need the result to go through, how much stronger than such is this conjecture?
Which orthogonal vectors?
No, the conjecture that orthogonal vectors doesn't reduce to through some all pair shortest path. It's a non-deterministic version of this strong exponential time hypothesis.
How believable?
Or not?
Well, so the question is how believable it is?
Yeah.
Yeah, so I think it's definitely less believable than strong ETH, and if you add randomness to the non-determinism, all of a sudden you can refute it. So there's just a de-randomization step that's missing that would refute the conjecture that they're basing this stuff on. So you can think of it as not necessarily that these problems can't be reduced to each other, but it would require some non-trivial technique to be able to do that. So thanks. I grant. Okay. All right. Good. Okay, so let's get to the reductions. The type of reduction we use is a special type reduction that we call fine-grained. So now, suppose I have two problems, A and B, and A has an algorithm that runs in A of n time, and B has an algorithm that runs in B of n time, and these seem to be sort of algorithms that we can't improve for whatever reason. And we want to show that the reason why we can't improve on them is roughly the same. And so we reduce problem A to problem B, showing that if beating B of n time for B, if you can beat B of n time for B, then you can also beat A of n time for A. So this is the idea of the reduction. So let me give you a definition now. Okay? So remember A of n and B of n are functions, and we say A is AB reducible to B if, okay, if you have an algorithm that takes an instance of problem A, and this algorithm runs in A to the 1 minus delta time for some constant delta, and produces instances of B. And you can think of these instances as we're going to ask an oracle for B on these instances. Now, this reduction can produce the instances adaptively. So it can produce the second instance after it learns what the answer of the oracle is on the first one, and so on. So it could be adaptive. So now it takes an instance of A, produces these instances of B, and it has this condition that the sizes, let's say the sizes of these instances of B are n1 to nk, then the sum of B of n sub I to the 1 minus epsilon is less than A of n to the 1 minus delta. So this condition, what it says is that if I had a substantially faster than B of n algorithm for B, then I could just run it on these instances of B, and the runtime will be the sum of I of B of n to the n sub I to the 1 minus epsilon, which is the left part in this inequality. And this inequality says that the runtime is bounded by A of n to the 1 minus delta. So this means that I can compose this algorithm with the original reduction and show that a B of n, a better than B of n time algorithm for B also implies a better than A of n time algorithm for A. One thing you should notice is that the epsilon and delta can be different. So for every epsilon there exists a delta. It doesn't mean that delta is equal to epsilon. In many reductions they will be equal, but sometimes we actually get a loss. What we're trying to do here is not to show that the runtimes are exactly equivalent, but to show that this place where we're stuck is related. So the two places where we're stuck are related. So improving on one implies an improvement of the other. So this is a type of reduction we use. Okay. So implications again: if B is in substantially more than B of n time, then so is A. We focus on the exponents of the runtime. A and B do not have to be polynomials. If they are, it looks nice. If they're not, I mean, you could still relate. You can relate exponential time problems like this. Let's say I have a 2 to the n algorithm and a 3 to the n algorithm for two different problems. You could still follow this framework. And what we're trying to do is eventually yield some equivalences, and these equivalences could be between a 2 to the n time problem and a 3 and an n cubed time problem. So it's an interesting place that we're at. Okay, and this is the key notion in the hardness theory for P. And we just make this type of reduction do as much work as possible. Okay, I will give you one example of a reduction in this talk, and it will only produce one instance, but in general, you can get a lot of leverage from producing many instances of the problem B. Okay, questions?
In any of the results so far, do you have to use can you leverage the adaptivity of the reduction?
Yes. We have a very nice reduction from all-pair shortest paths to a triangle problem, and there you crucially need the adaptivity. So there's a few other examples like that. Yeah. Okay. All right. So in the end, so the third part, I will show you what we know. Okay. So here's it's not a complete picture, but a pretty good picture of what we know. So let's consider the middle three problems. Those are orthogonal vectors, all pair shortest paths, and three-sum problems. Okay, And we know that K-sat can be reduced to orthogonal vectors via Ryan's reduction. So that's the dark green thing here, K-sat for OK. The arrows mean reductions. So what do they mean? So it means that an arrow from a problem A to problem B says that I can reduce problem A to problem B. The runtimes here in red say that would say what we're competing over. So for orthogonal vectors, we're trying to improve on n squared. For K-sat, we're trying to improve on 2 to the n. So basically, yeah. And the improvements here are in the exponent. Okay. So what's known? Let's start from threesome. Threesome is the oldest conjecture that people in computational geometry have used for many years. So in computational geometry, they assume threesome is hard, so you can't improve on n squared, and they've shown that many other problems in computational geometry, for example, the 3 points on the line problem that I mentioned earlier, it's threesome hard, and there's just a really huge literature there. Recently, we've also started basing the hardness of string problems on threesome. So there are some problems like local alignment and jumbo indexing that are hard under the threesome conjecture. Okay, for all pair shortest paths, we have something really special. Unlike the other two problems that we're basing hardness on, all pair shortest paths actually has an equivalence class. So we have shown, for example, that computing the radius of a graph, median of a graph, something called a negative triangle, and many other problems are actually equivalent to all pair shortest paths under subcubic reduction, for fine-grained reductions that care about n-cubed runtimes. Okay. Orthogonal vectors. Orthogonal vectors and the strong exponential time hypothesis that implies it. It implies a lot of hardness results that recently have been growing and growing. For example, in 2013, I had a paper that showed that even approximating the diameter of a sparse graph requires n squared time, assuming the orthogonal vectors conjecture. And later, there have been many other results. One of the most celebrated results was showing that edit distance is hard under orthogonal vectors. This was by backwards and Indic, and there were lots of follow-ups. For example, we showed the longest common subsequence, dynamic time warping, and so on, also has this hardness. And finally, all of these three problems imply very strong lower bounds for dynamic problems. This type of research was started by Petrashko in 2010, and he based the hardness of dynamic problems on the threesome conjecture. And then with my student Amir, we continued this idea, and we based the hardness of dynamic problems on all three of these problems. And it turned out that a lot of these problems have hardnesses under different subsets of these. All right, so this is basically what we know. And now the question is, can we actually get more believable conjectures? So we have three of them here, but why these? And why can't we just take something that we really believe? I know some people don't believe that orthogonal vectors requires n squared time. Some people think threesome should clearly have a subquadratic time algorithm, and so on. So can we find some conjectures that people would agree on a little bit more? So this is what I'll tell you in the rest of my time. So first, I'll spend just 1 or 2 minutes on two problems that are harder than all three problems we've been basing hardness on. Two very simple graph problems that are harder than CNF set, threesome, and all pair shortest paths. And then I will tell you about a very hard problem, a longest common subsequence. Namely, it's harder than we believed before. So this is probably a good time for more questions. Okay, let's start with the first one then. Okay, so this is, okay, you can't see this, but this is Aboud, me, and Huacheng Yu. What we did was we showed reductions from threesome, K-sat, and all pair shortest paths to two very simple problems in a graph. And these problems are asking questions about the triangles in a graph. So let me tell you. So the graph will have colors on its nodes. It won't have any weights or anything. So we showed, for example, so all of these can be reduced to both a problem called matching triangles and a problem called triangle collection. So I'll define what these are so you can see. Matching triangles is the following problem. You're given an n-node graph and a color for every node and an integer d. It's asking, is there a triple of colors such that there are at least d triangles in G with exactly these node colors? So here's a picture. Is there a triple, for example, pink, red, and blue, such that when I look at the graph induced by these colors, this graph has exactly the color, at least d triangles that have node colors pink, red, and blue. So this question has a trivial n-cubed time algorithm where n is the number of nodes. You enumerate all triples of nodes. You count the number of triangles for each color triple, and so on. Okay. It turns out that if you improve on n-cubed for this problem, then you resolve all three conjectures simultaneously. So threesome will be in subquadratic time, k sat for all k will be in less than 2 to the n time, and all pairs of the space will be in subcubic time. Okay, here's another one, also pretty simple. Now again, Sorry. Hello?
Assume here that the number of colors is order n, or is this still part if the number of colors is small?
That's a good question. So when the number of colors is small, it becomes easier, and you can think of the number of colors to be order, theta of n. Yeah, this is the hard instance has theta of n colors. Yeah, great question. Okay, you can also ask what happens when d grows. For matching triangles, it becomes n-cubed hard when d is roughly logarithmic. When d is a constant, we have subcubic algorithms, and their runtime grows as d grows, and we can show lower bounds and upper bounds almost matching. So anyway, it's an interesting problem. So here's another one. Triangle collection. Now you're given an n-node graph, and again, colors on the nodes. You want to know if there's a triple of colors that has no triangles. Okay, instead of asking, is there a triple with at least d triangles, I'm asking, is there a triple of colors that has no triangles? We call the triangle collection because we were saying, well, the triangles are going to collect all the triples, but this is really the nice definition. Okay, so this is nice. So we had some reductions to these problems, but reductions themselves, even though they're interesting, they wouldn't be as exciting unless we actually have conditional lower bounds from these problems. So again, I want to mention these problems don't have any weights of them. All pair shortest path and threesome, they seemed hard because of the numbers in them. In these problems, there's no numbers. And if you have a reduction from either of these problems to some other problem, then this problem will be hard under all three conjectures. So it's strictly more believable. Now we can think about the conjecture that at least one of the original ones is true. All right, so here's how the picture grows. So we actually, this is the reduction. We showed that triangle collection is harder than all of these, and it turns out that we can also show reductions to showing hardness for many dynamic problems and also versions of max flow. So this was the first attempt at getting a more believable conjecture.
But you can't, I mean, how does these triangle problems, how do they differ from all because you have these 3 new red arrows, right? But before you already had the 3 yellow arrows that were pointing to the dynamic problems.
Yeah, but
now you keep something in between, right? But
so these are not to all dynamic problems. There exist some dynamic problems in this red subset that are hard under all 3. So before we had reductions to some problems from orthogonal vectors, to some from threesome, and to some from all pair shortest paths, but now it turns out some very basic ones are hard under all 3.
What's a simple example of a dynamic problem? I'm not sure.
Okay, so here's a problem. I give you a graph and 2 nodes, okay, and I want to do updates, insert and delete edges, and I want to know if T is reachable from S.
I see, okay.
And there's some other ones like this. So very, very simple, but
okay, all right. So,
and then the lower bounds are for the update and query time, then there's some trade-offs.
All right, thanks.
No problem. Okay, so this is some picture. So I want to, I was actually planning on having an hour, but then I realized it's 15 minutes. I hope I can go a little bit over. Is that okay? Or...
Yeah, sure.
Yeah?
Sure.
Okay,
yeah.
Thanks. Okay, so I will...
You still have, I mean, right now you have 20 minutes, and if you need...
Oh, 20. Great. Okay, 20 is enough. Okay, thank you. Okay, right. I was worried. I thought I might have 10, and then it would be very hard. 20 is good. Okay, so what I've given you an introduction, and I showed you 2 problems, and now you can try to prove hardness from, and they will be really, they seem very, very hard. And now I'm going to tell you about a conjecture that is that looks at strong ETH and tries to make it even more believable. And we'll show that for this conjecture, longest common subsequence and other sequence similarity measures require n squared time. Okay, so let me tell you a little bit. Okay, so we'll be talking about circuits. So let's talk about strong ETH first. So strong ETH is a problem, is a conjecture about the hardness of CNF SAT. And CNF SAT is a circuit satisfiability problem, which talks about linear size depth-2 circuits. Okay, CNF formulas. Okay, and these are very, very, very special types of circuits, and it's saying that the circuit satisfiability problem for those very special types of circuits requires essentially 2 to the n times. So essentially the brute force runtime. But you know, there are more difficult circuit satisfiability problems. We don't have to restrict ourselves to linear size CNF formulas. So what about general circuit SAT? So taking an arbitrary, very, very complex circuit and asking to solve its satisfiability, that should be harder. You know, we believe it's much harder than solving CNF SAT. And even if we restrict the circuits a bit more, so look at NC circuits. These are circuits that have polylogarithmic depth. So these are also much more complex than linear size CNF formulas. And also NC1 SAT, even if we only care about log n depth, even then it's much more complicated than CNF formulas. So if we could base the hardness on of problems on the satisfiability of one of these more complicated circuit SAT problems, then this should be a much more believable hardness. So we define this circuit strong ETH version. So you're given the circuit class C, for example, NC, and we say that satisfiability of circuits from the circuits class on n variables and size S requires 2 to the n minus little of n times poly S time. So this is a strict generalization of strong ETH, and it should be much more believable as when the circle class includes linear size CNF formulas, for example, for these. Okay, and so our goal is now trying to take these problems that we knew that were hard under strong ETH and seeing whether they may be hard for a harder circuit satisfiability problem. Okay. And another compelling reason why we would want to look at this is because Ryan had this nice result that said that if you have a fast satisfiability algorithm for some circuit type, then even if it's only 2 to the n over n to the 10, then you immediately get circuit lower bounds for classes such as e to the np and so on. And the bigger the class for which you solve the satisfiability problem, the stronger the circuit lower bound. So, and when we get such a circuit lower bound, it might be something we believe is true, but it's something that is very, very hard to prove with current techniques. So if we show that, for example, longest common subsequence, if getting a better than n squared time algorithm for it solves circuit SAT for very large complex circuits, then we immediately get a circuit lower bound out of it from Ryan's result. So, and this should convince a lot of people that it would be hard to improve an n squared time algorithm. So this is what we're heading at here. Okay, so let me tell you what we prove. This is a very recent development. We show the following theorem. there's an efficient reduction from the satisfiability of non-deterministic branching programs. I'll define what that is. Of size t and width w and n input variables, and you can take one of these branching programs and reduce it to any one of the following string problems, and you obtain strings of length 2 to the n over 2 times t to the order log w. Okay, so I need to explain what this is. Barrington in '85 showed that branching programs with this t parameter roughly 2 to the polylog n and the width parameter roughly exactly 5, it captures the class NC. Okay, so in particular, our reduction shows that you can take n, circuit SAT for the class NC and reduce it to these problems: longest common subsequence, edit distance, and so on. And what it would show is that if you can solve any one of these problems faster than n squared time, then you will refute the NC version of strong ETH. Okay, so this is our theorem, and I will try to give you some intuition about how to prove it. Okay, so let me tell you a few more consequences. So more consequences of this theorem is that is the following: you get very, very impressive satisfiability algorithms. So for example, suppose I take branching programs where the size, it's 2 to the literal of square root of n, n is the number of variables, and w, the width, is 2 to the literal of square root of n as well. These branching programs can represent any non-deterministic Turing machine that uses literal of square root of n space. So it would give a fast algorithm for these problems would give a very non-trivial improvement over exhaustive search for satisfying such complex objects as these non-deterministic Turing machines. And these objects can implement lots of very fancy things, for example, cryptographic primitives. So you would get something that something very surprising, and this is much more surprising than just refuting the strong exponential time hypothesis. Okay, one more. Just following Ryan's work of algorithms implying circuit lower bounds, you get that if these problems, edit distance, longest common subsequence, and so on, if they have a subquadratic time algorithms, then in particular the class e to the np does not have the following types of circuits. It doesn't have 2 to the literal of n size Boolean formulas, non-uniform. And my complexity friends tell me this would be a very nice result, because we don't even know if the much bigger class sigma 2 x has even 2 to the literal of n depth 3 circuits. So this would imply very, very surprising results, things that people don't know how to prove right now. And also, it would imply that this class doesn't have literal of n depth circuits of bounded Fanon, or 2 to the non-uniform 2 to the literal of square root of n size non-deterministic branching programs. So it would be very, very, very surprising if you do it. It requires some very interesting techniques. So it was good. It's important to work on these problems, and undergrads, when they try to work on longest common subsequence and improve on the dynamic programming algorithms, they're proving circuit lower bounds for e to the np. So that's good. Okay, so finally, one of the more exciting things that comes out of this work is that it's something we call a polylog shaved as a lower bound mate. Okay, so what is this? We know that for many problems we have been able to shave polylogs over the runtimes. In particular, some recent work by Ryan and students showed that all pair shortest paths and orthogonal vectors, you can shave all the polylogs off the runtime. So you can get an n cubed over some function time algorithm where the function is bigger than a polylog for any polylog. And now the question is, can you do this for these problems? Can you do it also for edit distance and longest common subsequence? And recall that these problems have n squared over log squared n time algorithms. So you can shave something. Can you shave all the polylogs? And it turns out that because of our reduction, if you can shave all the polylogs, then this class e to the np is not an NC1. And this isn't something that we believe is true, but we don't know how to prove. And it's also meaningful for particular polylogs. Let's say I want to shave log to the 1000 n. Then if I am able to do that, then this class doesn't have non-uniform Boolean formulas of size n to the 5. Now this 1000, you can improve it. You can bring it down to, I don't know, something smaller, maybe 10. But anyway, it just follows from my reduction. So in shaving any, any log to the C for some large enough C will give you a new circuit lower bounds people don't know how to prove. Okay, and the question is, can we bring this down to log to the 2.1, because then it will be roughly tight. Then we'll show that n squared over log squared then is tight for under some, unless some breakthrough comes. Okay, so these are all the consequences that we can derive from such a reduction, and I'll tell you a little bit about the reduction, hopefully it follows. Are there any questions until now? Okay, so here's the theorem again. We take branching programs. What are branching programs? They're layer graphs. There's a start node and an accept node. The start node is S, the accept node is T. Start node starts in the very first layer. The accept node is on the last one. You can think of each layer being labeled by a variable, and an edge out of a node says what the assignment to this variable is. So and then the way you evaluate such a program on an assignment, say I have assignment to all the variables x1 to xn, then I start at the start node, maybe it's labeled by x1, and then in checking my assignment is x1 0 or 1. If it's 0, you go on an edge that's labeled by 0, and if it's 1, you go by an edge that's labeled by 1, and you follow, and you check whether you can reach the accept state. Because all right, so I got some message here, that's why I'm worried. It says we're required to vacate something.
Oh, it's nothing. Don't worry about the chat messages. I'll look at them. Someone had to leave, but it's
I see, sorry. All right, I got worried. Okay, so now we have this branching program and a start and accept state, and the question is, the branching program satisfiability problem is given this branching program, is there an assignment to the variables such that the start state can reach the accept state by following these arrows? Okay, in this particular case, the assignment 0, 0, 1, x1 equals 0, x2 equals 0, and x3 equals 1 follows this path. And it actually leads to the accept state. Notice that the number of layers T can be much bigger than the number of variables N. So in particular, variables can appear many, many times. For example, x1 appears many times. Okay. And this problem is particularly interesting when W is 5. So, okay, let's move on. Now, again, we have this. And I'll just give you a simplified proof that's restricted to the longest common subsequence. The paper itself has a more complicated thing that can handle a large variety of sequence problems. So here's the idea. You start with the branching program, and we're going to take the variables that it works over, and we're going to split them into two halves. The first half will be U, the second half will be V. And then we're going to look at all possible partial assignments to the variables in U and the partial assignments to the variables in V. There's 2 to the n over 2 of these. Okay? And now what we'll do is we'll consider the following branching program pair problem, which asks, is there a partial assignment A to the variables in U and a partial assignment B to the variables of V, such that together they make the branching program accept. So together they form a satisfying assignment. And now this question, its input is 2 to the n over 2. And so we're trying to solve this in subquadratic time. Okay? The input is now 2 sets of partial assignments, and we want to check if you can pick one here and one from here and put them together and make the whole thing satisfy. So for example, let's say I pick b, the partial assignment to the variables x2 and x3 to be x2 is 0 and x3 is 1. And when I pick this partial assignment, this will actually delete a bunch of edges and will restrict the branching program in some layers to some red edges, like here in the picture. And what I'm asking is now, can I pick another partial assignment to the other variables, so that when you put them together, you have a path between S and T.
How many variables are unassigned in these partial assignments?
So both sets have size n/2, so you're assigning n/2 of them. You're splitting the variables in half, so now it becomes a pair problem. And you're trying to solve it into n to the 2 minus epsilon n time, because the input is now of size 2 to the n/2. And so we'll start, instead of starting from branching program set, we'll start from this branching program pair problem and reduce it to longest common subsequence. Okay, so now it's a problem in polynomial time. Okay. Right. Okay, so the reduction proceeds like this. You take branching program set, reduce it to this branching pair problem that I just mentioned. Then you take this branching program pair problem and reduce it to a problem called longest common subsequence pair. And then there's a reduction that Amir and Artuz and I had, and it shows that the longest common subsequence pair problem can be reduced to longest common subsequence. So let me tell you what LCS pair is. You're given sets in A and B of sequences over some alphabet, and every letter in the alphabet has some weight. You're also given an integer weight, W, and you want to know if there's a sequence in A and a sequence in B such that the weighted longest common subsequence has weight at least W. So what's the weighted longest common subsequence? Instead of looking at the number of letters in a subsequence, you sum their weights. So you want to maximize the weight of a common subsequence. For example, if I take the sequences 0, 0, 1, 0, 1, 1, 0, and you know, in A and then in B, I have these examples, and let's say the weight of 0 is 2 and the weight of 1 is 1, then you look at what the weighted longest common subsequence of these two sequences is. So a common subsequence is, for example, 0, 1, 0, 1, 1. And when you sum up the weights become 7, and it turns out this is the largest weight common subsequence. So that's what. So the pair problem is you're given two sets. You want to pick a sequence from each set, and such that their weighted common subsequence is maximized. So the weight of the common subsequence is maximized. So this is the question. And we had a reduction from this question to LCS such that if the size of the sets is n and the sequence length is d, you get an instance of LCS of length n times poly d. Okay? So now when you bring it up here, what's going to happen in our reduction? You take a branching program of n variables, so size t with w, you produce this branching pair thing of 2 to the n/2, and then t and w. Then we have a reduction, which I'll mention, which goes to LCS pair. It gets also 2 to the n/2 sequences. The length of the sequences is t to the order log w, and then the reduction that reduces this to LCS produces a longest common subsequence problem of length 2 to the n/2 times t to the order log w. Okay, so this is how it proceeds. Yeah.
So the reduction from LCS pair to LCS does not depend upon the size of the weights.
It does. Yeah, it does. So basically, the weights. So
Linear
the reason why so the weights will be very small. So that's why. But yeah, in the reduction, you have the weights appear as a multiplicative factor, the size of the weights.
Yes.
Yeah. Thank you.
So, Virginia, can you just give us a sense of where you are in the talk? Like how much time you just?
So I can finish now, but then you won't see the reduction.
No.
Or I can spend 10 minutes and show you the reduction. So that's the question. Do you want to finish now, or do you want to?
No, I think we want to see the reduction. It's just in case sometimes people have to leave at the end of the hour, so maybe if.
Yeah. So
wanted to see
if anyone
what the
wants
plan
to
is.
leave, this is fine. So the plan is as follows. So basically, there's this red arrow that appears here. I was going to show you how this works, and I can give you a brief summary if, in case you need to go. So the brief summary is we use an approach that is like Savage's theorem, and we produce some gadgets that will correspond to the sequences in this LCS pair thing. The gadgets talk about reachability between two nodes in the branching program, and in the end, the final gadget will tell us whether S and T are reachable if we put two pairs of partial assignments. So that's how this thing works, and what we do is we create OR and AND gadgets. So in particular, you can use these gadgets to start from formula set instead of branching program set. But yeah. So it turns out that longest common subsequence and many of these other problems actually can implement AND and OR. So in a certain sense. So that's the punchline. So I will need 10 minutes to actually give you all the details, but yeah.
Yeah, that's perfect. It's no problem. Yeah.
Yeah? You okay?
Yeah, well, I don't know. I want to see it.
All right. Okay, so let's go. Okay, if anyone has to go, please do. You know, I realize that I'm running over, so okay. So I've never given this version of the talk before, so let's try.
Well, that's an advantage of the format. It's completely fine to run over. We're recording anyways, so.
Okay, that's great.
Go for it.
All right. Okay, so I'll go for it. Okay, so here's again what we're trying to do. We have this branching program pair question, which is asking about a pair of partial assignments that put together have a satisfying instance of branching program. So there is a path from S to T. And we also have this LCS pair question. We're given two sets of sequences. We want to pick one sequence from each set so that together they maximize the weighted longest common sequence between them. So those are the two questions, and what we do is we create gadgets, and the gadgets are just sequences. And these gadgets, there's two gadgets for each pair of nodes in the branching program, and they will talk about whether you can reach V under partial assignment A, and whether you can reach V under partial assignment B. And so the gadgets are G sub U. Big U says which part of the variables we're setting. And the subscript is two nodes, U and V. And K is basically the logarithm of the distance between these two nodes in the branching program. And we only be looking at pairs of nodes that are at distance that's a power of 2. So if I have U and V and two layers of the branching program that are distance 2 to the K, then I will talk about them as gadget, GUVK. And the gadget depends on the partial assignment to the variables in U or the partial assignment to the variables of B. And the condition is that if, once I create these gadgets, these are some sequences, their weighted longest common subsequence is exactly some value, Y sub K, if you can reach V in the branching program restricted to the partial assignment A, B. And otherwise is strictly less than Y sub K. So, so the longest common subsequence of these two gadgets, one for the partial assignment A and the other one for the partial assignment B, when you look at what it is, it will tell you whether you can reach V when you put A and B together and form a complete assignment to the variables. Because this is what we'll do. There's some gadgets, okay? And the base case is relatively simple. So K equals 0 is when U and V are in the neighboring layers of the branching program. We'll check whether there's an edge between U and V. If there isn't, we won't do anything. But if there is an edge, this edge is labeled by some assignment to a variable. Let's say it's X sub I equals Q. And then we'll create the following sequence. There will be only one letter. So GUV0 of the partial assignment A will be 1 if A is consistent with the assignment. So either the variable is in the variable set corresponding to the partial assignment, and this partial assignment says that this variable has to have value Q, or the partial assignment is to the other set of the variables. In both cases, the partial assignment is consistent, in which case we'll put a 1, and otherwise we'll put some other letter, either phi1 or phi2, depending on which set of variables we're working with. And these phi1 and phi2 only appear here. So when you look at what this is, you get, and you put all the weights will be 1. So then you get that the longest common subsequence of these two gadgets is 1, if and only if there's an edge between U and V, and the partial assignments A, B together are consistent with that edge. So if U can reach V and A, B are consistent with the edge, there's a typo here. So, okay. It should say that the weighted longest common sequence is 1 whenever both A and B are consistent with the edge, and otherwise is 0. So this is a base case. So the base case produces sequences of length 1 and weight 1. Okay. Yeah.
Can you say again? What does it mean that both A and B are consistent?
So,
taken care of by one of them.
So what does it mean for both A and B to be consistent? So suppose the variable I'm looking at is x1, and the edge says that x1 has to be 0. So now a partial assignment is either a partial assignment to the first half of the variables or to the second half. Now if x1 appears in the first half, then the partial assignment that assigns assignments to this first half has to say that x1 is exactly value q, and then it's consistent. If it says it's not value q but it's not q, then it will be inconsistent. And it will be b if it assigns values to the other set of the variables where x1 is not in, then it will always be consistent with this assignment.
Okay, gotcha. So one of them is always 1, the other one might be the one of the 3.
Yeah. Okay. Yes. Exactly. Okay, so this is the base case. Here's the general case. This is the idea. So look at U and V. There's some distance to the k. Okay, and there's some layer in the middle. Okay, that has W nodes, and there's a path of length 2 to the k minus 1 from the layer of U to it, and the path of 2 to the k minus 1 from to the layer of V to it. Okay, so this is in the middle, and there's a path between U and V if and only if there's a path from U to one of the W's, and from that W to V. And you have a big OR over all the W's and an AND between all of them. So this is what it is, and now we have to implement it using sequences. Okay. And what we will actually show is how to implement AND and OR using sequences. Okay, so here's what we want to do with these AND and OR gadgets. So let x and y, x1 to xk and y1 to yk, be some sequences. And in particular, for each one of the i's, when you take x sub I and y sub I and look at their weighted longest common subsequence, it's always less than some value y. And we can think of the weighted longest common sequence being equal to y to represent the Boolean value 1, and less than y to represent the Boolean value 0. Okay, so this is what we'll be looking at. And we'll construct these gadget sequences AND and OR, and they're subscripted by the set of variables we'll be looking at, such that if you look at the ANDs, when you take the AND of sub U of x1 to xk and the AND sub V of y1 to yk, and you take the weighted longest subsequence of them, it will be exactly y prime if for all of the i's the weighted longest common sequence equals y and is less than y prime otherwise. So it's implementing AND. Okay. In the other case, the OR is going to say it's going to be equal to some y double prime if there exists an I, such that for which xi and yi have longest common sequence equal y and less than it otherwise. Okay, so Boolean value 1 is equal to the maximum possible longest common subsequence value. Boolean value 0 is less than it. So this is how we implement these, and I will give you some idea of how to do it. And after you have AND and OR, it's very easy to implement this reachability thing. Okay, you just compose OR over U of AND U of the AND of for each W in the middle layer. You take the ANDs, and then you take a big OR out of them. And you will see that once you have the ANDs and OR, you will get the weighted longest common subsequence is equal to some value if and only if there exists a W such that both U reaches W and W reaches V when you look at A and B being the partial assignments. Okay, so this is the goal. And I have 2 more slides. Questions? Okay. So finally, the goal will be if the X sub i's and Y sub i's, these sequences all have weight W, then the AND gadget will have weight roughly K times W, where K is the number of these pairs, and the ORs will have weight K squared times W. So what will happen is if the branching program has length T, I have to do this basically T times, and each time I do it, I multiply by at the most K squared or K cubed. And so I get K cubed to the T, to the log T essentially, but K is actually the width, because this is in our reduction, the number of things for which we have to take the OR on is the width. Okay, so that's the thing. Okay, so here's AND is very easy. So we only care about ANDs of 2 sequences, so I'll just show you that. The AND of 2 sequences is you pick a new symbol, pound, that doesn't appear anywhere else, and it has weight 2W, where W is the length of these sequences X1, X2, Y1, Y2, Y2. And the AND gadget is there's X1 pound X2 and Y1 pound Y2. And the pound symbol is much heavier than X1 or X2. And so what you get is that you have to match the pound with the 2 pounds together, and then you get then you're matching S1 with Y1 and X2 with Y2. And so the weighted longest common subsequence of the 2 AND gadgets is exactly some value, namely 2W, the weight of the pound, plus the weight of the 2 matches of X1, Y1, and X2, Y2. And so you'll get equality if and only if both of them are equal to Y, and otherwise you get something less than that. So AND is particularly easy. And you can, if you wanted to do an AND of more than 2 pairs, you could, more than 2 sequences, then you could, you could just repeat, put many pounds, and it will still work. And the total weight only gets, is only 4W here. So, right. Questions here? Okay. OR. So this is probably the final one. Okay, so the OR, now you're given 2 sets of sequences, X1 to XK, Y1 to YK, and we want to get these OR gadgets such that the longest common subsequence of the OR gadget says whether there exists an I such that Xi and Yi together have weighted longest common subsequence exactly equals to Y. And otherwise less than Y, double prime. So, and the condition is that for each I, the weighted longest common subsequence of Xi and Yi is less than or equal to Y. So you want to detect whether there is a pair Xi and Yi where there is an equality. So equality, remember, represents Boolean value 1. And the way we do this is kind of funny. So what we do is we take the X variables and we kind of split them up. We put some padding in between them. We have these new symbols, FG and sub I. So the F's, you start the sequence with f repeated 2k time and ended with f repeated 2k time. And in the middle, you just sort of repeat g, n sub I, x sub I, n sub I, g. And you repeat it over and over until you exhaust all the x sub k's. So this is the first sequence, and the second sequence is a little bit different. So here we take, for each y sub I, we enclose it in f, g repeated 2k times, and n sub I, and then n sub I, g repeated 2k times f. So these chunks are sort of repeated like this. And let me show you why we want this. So first of all, we set the weights of f, g, and n sub I to be much bigger than the weight of any one of these subsequences. The weight is at least, let's say, 9w, where each of the x sub i's and y sub i's are of weight at most w. And what will happen is that we have to match all the f's, and then we have to match all the g's, and then we have to match some of the n sub i's. So in the bottom subsequence, there are exactly 2k f's, and all of them need to be matched, otherwise you'll be losing a lot of weight. So what happens is now, some of the f's will have to be matched to the first 2k f's in the first gadget and some of them in the second. And what this does is actually selects a single y sub I in the bottom sequence. Basically, once you stop matching with the left part, you start matching with the right, and in the middle there's a single y sub I you're selecting from the bottom sequence. Okay, after you've done that, in the top part, the part that still needs to be matched, there's exactly 2 kgs. And they all need to be matched because they're very, very heavy weight. And if you miss one of them, you're losing a lot. So then what you end up doing is matching some of them to the first 2 kgs and some of them to the second 2 kgs. And then what this does is select some x sub j to map y sub I to. Okay, so now we've selected x sub I and y sub j. And it turns out that these have to be exactly the same because these and sub I symbols are heavy. So if you don't match exactly the same ones, then you're losing a lot of weight. So what happens is actually you're picking, for some I, you're picking x sub I and y sub I to match to. And the rest is a fixed number that you're getting for the weighted longest subsequence. So the gadget weight is k squared, where k is the number of pairs x sub I, y sub I, times the weight w, which is the weight of one of these sequences x sub I. And this gadget weight only depends on the longest common subsequence of x sub I and y sub I. And so basically this gadget maximizes the weighted longest common subsequence of x sub I and y sub I over all I. And so this is how we implement OR. So if the maximum over these x sub I, y sub I is exactly the original value y, then we get this exact value y double prime, otherwise you get less than that. Questions? So the option, yeah.
So you're saying you want all f's to be matched?
Yeah, all the f's from the bottom have to be matched.
Oh, okay. So there are 4k of them, but only 2k are really matched.
Yes, only the 2k ones from the bottom need to be matched, yeah. And we use this gadget of putting 2k on the left and 2k to the right to say that some of them will be on the left, some on the right, and we'll select something in the middle.
Thank you. Thanks.
No problem. And similarly, the g's, only the ones on top have to be matched. And those select the top x sub I. And then we put the only reason for these and sub j things that are around the x sub i's is to make sure that we're matching x sub I to y sub I and not some other x sub j to y sub I. That's the only reason for these. Yeah. Okay, so this is how you implement OR. and was very easy. And you put them together, you look at what the weight of the final gadget is, and it turns out to be the width to the order log t, because we only have to run it log t times. Okay, just like in Savage's reduction. And so in the end, we get this result. So I showed you this middle reduction. The other two are pretty simple. And in the end, you can do branching program set with n, t, and w. You reduce it to longest common subsequence of length 2 to the n over 2, t to the order log w, and you get your all the consequences. Since we can do and or, we might as well have started from formula set instead, so you can do that too. But it doesn't really give you, it gives you roughly the same parameters. So yeah, I like to think about reachability, so it's nice. Okay, so that basically ends it. This is the last thing. See, there's this thing saying that what we did was actually we split the problems that you can reduce orthogonal vectors to ones that you can make much harder. So all these sequencing similarity measures are now hard under this branching program set problem, and then I can say thanks. That's all. Thanks.
Thanks, Virginia.
Thanks, Virginia.
Sorry for running late. So hopefully it was okay.
Yeah, it's no problem.
Yes, yes.
So do we have questions? Okay, just a general question. So this is very recent work, right? And you introduce these hard problems there, and you have these reductions to the LCS. So what's your feeling about the general picture? Could you, is there something distinctive that would, I mean, that this would remain localized, or you think you can get more out of it, or?
It's a great question. I don't think it's localized. I think there's something general going on. So we can start thinking about these circuit classes, right? I defined the circuit strong ETH thing. So you can.
Sorry, do you mind just popping up the slide? It's I want to stare at it. Yeah, okay, thanks.
Which one?
No, the one with the picture. The last one.
Okay, this one. Okay.
Yeah, because as you mentioned problems, it's easy to. Okay, sorry, thanks.
Okay, so so for example, diameter, I'm not sure if you can make it as hard as these problems, as longest common subsequence at a distance. I think diameter is actually, I think it's easier.
So could you imagine? Sorry. Yeah. Earlier you had something that distinguished between the three problems, right? Orthogonal vectors, tree sum, and APSP by using this non-deterministic reduction. So, so you think you could have similar?
Oh, I see. Showing that you can't.
I mean, it just sounds hard to show that you cannot have a reduction, right?
Yeah, it's hard. It's kind of, yeah, it's not very easy to show it formally, but I believe. Okay, if you believe that satisfiability for complex things like NC circuits and so on is actually harder than linear size CNFs, then you should believe that these problems are much harder. So you can conditionally say that, yeah, I think we should, a lot of these other problems like diameter, for example, even orthogonal vectors, I don't see how they can even implement OR. Okay, so they can implement one OR, but implementing a general OR, it seems hard to do. So so this is just a feeling. I don't have a formal proof, but I think we can't.
So far, are there any two classical problems for which people are able to demonstrate that they are stuck for the same reason?
Well, these reductions show some of these things, right? Because the reductions are relatively simple. They don't use any fancy techniques. Okay, so it seems like if, for example, for the equivalences, right? We have this class of equivalences between all pair shortest paths and these other problems like radius. So I think you can view these equivalences as saying that that's why we're stuck for the same. They're stuck for the same reason, right? The reductions don't do anything fancy. They're just...
No, I mean, are there two problems for which you are able to give reductions in both directions?
Yes, yes.
Okay.
All pair shortest path, radius, median, betweenness, negative triangle, second shortest path, shortest cycle, many.
Okay.
So we have an equivalence class around all pair shortest paths. Yeah, there's a few problems equivalent to threesome, and some problems are equivalent to orthogonal vectors, but there aren't such nice equivalences there. And which is actually why we could show that longest common subsequence is so much harder, because it wasn't equivalent to orthogonal vectors. I believe orthogonal vectors is a much simpler problem.
Okay. Has randomized reductions been considered in this setting?
Yes, yes. So I allow randomized reductions. Yes.
Okay.
And in fact, yeah, some of these can be made simpler when they're randomized. Yeah. Yeah. Any reductions are nice. But then you have to assume a stronger hypothesis that, let's say, that SAT requires, K-SAT requires to the n time even with a randomized algorithm. So you have to assume that then.
I have a quick question. So maybe I missed that. What do you think is the relation between the orthogonal vector problems and the triangle problems you defined earlier?
You mean matching triangles and this and triangle collection? So I think the triangle problems are strictly harder.
The triangle problems are harder than what I see. And one more question. So you just introduced this framework of fine-grained reductions, and did you use it for approximation problems? And if you did, then what are the plausible assumptions? What are the
Okay, great. Yes, so we have a few results in approximation, and they don't change the hypothesis. So we can base some hardness of approximation on these conjectures here. For example, for diameter approximation, you can show that improving on the 3/2 factor in subquadratic time refutes orthogonal vectors. And there's some other things for betweenness centrality where we also talk about approximation. But in general, it's much harder to prove approximation hardness. In particular, just focus on edit distance or longest common subsequence. We think it's hard to get approximation algorithms for these problems that are faster than n squared time, because it's just been there's nothing really known, but we haven't been able to show such hardness. And as you mentioned, maybe we need to have a different assumption, but I don't know what that should be.
Great, thank you.
So do we have any more questions? If not, maybe we'll
give a coffee now.
Offline. Well, let me thank everyone for joining us the whole semester of TCS Plus Talks. Thanks, Virginia, for the great talk. And we'll take a well-deserved winter break now and resume in the spring. So bye everyone, and thanks for joining.
Bye. Thank you.
Thank you, everyone.